Hi everyone! Today we're doing section 9.4, part 5. We're going to learn the alternating series test, and then we're going to define conditional convergence, which will be a new thing. So the alternating series test that says that if a sub n is greater than 0, so again, we're looking at an a sub n that is positive, and then you have an alternating series. So if you look at this definition, you can see the -1 raised to the n, or maybe -1 is raised to the n plus 1. And that's just changing if you're starting with a positive or a negative. Notice the a sub n is the rest of the definition here in this definition. They're saying the alternating series converges if both of the following conditions are satisfied. So the first one is that the limit as n approaches infinity of a sub n has to be equal to 0. And we know that's the case because the nth term test for divergence says that if this is not the case, then it's going to diverge. So you got to make sure that condition is satisfied. And then the second one says that a sub n must be decreasing, or that a sub n plus 1 is less than or equal to a sub n for all values n greater than k, such that k is in the set of integers. So this is basically just saying that a sub n has to be decreasing, and the limit as n is approaching infinity of a sub n has to be equal to 0. Note, this does not say that if the limit is not equal to 0, that the series will diverge by the AST. It's diverging by the nth term test, not the AST. So let's get into some examples. Let me make this a little bigger for us. Okay, so here in my first one, you'll notice I have an alternating series because of this -1 raised to the n plus 1. So we know it's going to be alternating. That means the a sub n is what's left. It's the n over 2n minus 1. So you need to check and first make sure that the limit as n approaches infinity of n over 2n minus 1 is equal to 0. And when I test that, I notice that it doesn't. It actually equals 1/2. So it fails that first condition. Therefore, the series diverges by the nth term test. Notice, not the alternating series test. The alternating series test is only for convergence. This fails the nth term test. So it diverges. Let's take a look at the next one. So here I can see my alternation with that -1 to the n, and a sub n will be equal to n over natural log of 2n. So my first condition, I need to look and check the limit as n approaches infinity of this a sub n. So as I test infinity, I get infinity over infinity. So I'm going to be using a L'Hopital's rule here. So I end up with 1 over 2n times a 2 when I'm taking my derivatives. And these cancel, and I'm left with the limit as n approaches infinity of 1 over n. Oh, it's 1 over n. Just kidding. So 1 over n, which is the limit as n approaches infinity of n, which is just a big old infinity. That is very far from 0. Therefore, we have another alternating series that is going to diverge by the nth term test. All right, let's take a look at the next example. So here, it's not super clear that you have an alternation, but take a look at what this is saying. If I plug in n equals -1, you'd have cosine of pi, which is -1 over 1. Then when I plug in a 2, I would have cosine of 2 pi, which is a +1 over a 2. Then you'd have cosine of 3 pi, which is a -1 over 3. Cosine of 4 pi is 1 over 4. So you can see what's happening is you're alternating in between 1 and -1 in your numerator. So really, this series could be written as n equals 1 to infinity of -1 raised to the n, because you want to start with a negative, all over n. And there you can see your alternating series. So my a sub n is 1 over n. So let's check that limit. So limit as n approaches infinity of 1 over n is indeed 0. And then you need to take a look at a sub n and ask yourself, is a sub n decreasing? as n approaches infinity. And it is. Those numbers get smaller and smaller and smaller. So therefore, this is our first series that is going to converge by the alternating series test. So you need to check two things. You need to check the limit, and you need to check that a sub n is decreasing. Let's look at some more examples. All right, so here in part D, I have the sum from n equals 1 to infinity of negative 1 to the n minus 1 all over n factorial. So you note that we have the alternation. My a sub n is going to be the 1 over n factorial. I need to check the limit as n approaches infinity of 1 over n factorial, and that is indeed 0. And then when I'm looking at a sub n, is this going to be decreasing? And it absolutely is. Therefore, the series will converge by the alternating series test. Let's take a look at the next one, E. All right, so here I have that alternation with the negative 1 to the n. My a sub n then is going to be 1 over n minus 5 quantity squared plus 1. So if I take a look at the limit as n approaches infinity of 1 over n minus 5 squared plus 1, that does equal 0, so I'm good there. But now I need to check and say, is this decreasing? Starting with n equals 1. If I think about what that denominator is a quadratic. If I think about this like a function, if I was going to graph f of x equals x minus 5 squared plus 1, I have a quadratic with a vertex at 5, 1. And then since it's a quadratic, it's a parabola opening up, right? So think about that denominator and think about what's happening starting at 1. I would be decreasing from 1 to 5 and then increasing from 5 to infinity. Well, think about what's happening. If the denominator, because this is just the denominator, if the denominator is decreasing, that would mean that the ratio of 1 over those values would actually be increasing from 1 to 5. So therefore, I cannot say that this right here, a sub n, is not decreasing for all n values from 1 to infinity. And it's actually not, I can say it's not decreasing specifically from 1 to 5. So therefore, the alternating series test is inconclusive, and I would need another test. So we're going to have to stay tuned for this one. I need another test. So put a star by this one, and I think we might have to come back to this one, maybe in section 6. But think about it in the meantime. Let's look at F. So I have the sum from n equals 1 to infinity. I have my alternation, and I have my a sub n would be 1 over n. So the limit as n approaches infinity of 1 over n is definitely 0. And then if I think about 1 over n, that is definitely going to be decreasing for all values from 1 to infinity. Therefore, the series converges by that alternating series test. And this one is special. We're going to actually come back to this one here in a minute because this one is special and it plays into what we're going to talk about next, which is conditional versus absolute convergence. So let me get this centered for everyone. So far we have not talked about anything but plain old convergence and divergence. But there's actually three different types of convergence. You have absolute convergence, you have conditional convergence, and then you just have plain old convergence like what we've been discussing. So let's look at the theorem. It says if a series from n equals 1 to infinity of the absolute value of a sub n converges, then the series from 1 to infinity of just plain old a sub n also converges. Such a series is called absolutely convergent. Notice that if it converges on its own, like it's just plain old convergence, the alternator only allows it to converge more rapidly. We also have a series that is called conditionally convergent if, without the absolute value signs, it converges, but when I add in those absolute value signs, it diverges. So let's look at some examples here, and then we're going to go back to part F of the last example. So here, take a look at this series. It's alternating, so I'm going to start with the alternating series test. My a sub n is 1 over the square root of n. I need to confirm that the limit as n approaches infinity of 1 over the square root of n equals 0, which it does. And I need to take a look at this and make sure that it is decreasing, which it is. Therefore, the series from n equals 1 to infinity of negative 1 to the n all over the square root of n converges by the alternating series test. But now I want to test for absolute convergence. And if I'm going to test for absolute convergence, what I'm doing is I'm taking a look at the series, and I'm going to take the absolute value of all of the pieces of my series. When I do that, what happens when I take the absolute value is this alternation here goes away. Negative 1 to the n, when I alternate, is always just going to be a 1, which will leave me with the series from 1 to infinity of 1 over the square root of n. And this, I know, diverges by p series. Therefore, the series 1 to infinity of negative 1 to the n over the square root of n is conditionally convergent. And what I have done here is I've proven that it's regularly convergent. Here in all of my black writing, it just regularly converges, but it does not absolutely converge, and therefore it is conditionally convergent. Let's take a look at this next example. Here, I notice that it's alternating, so I'm going to start with that test. I would have a sub n equals 1 over 3 to the n. You know what? I'm changing my mind. Let's go an opposite route. Changing my mind. So I can do alternating series test, but remember, alternating series test is only going to prove plain old convergence. Let's use this theorem up here, actually. So the theorem says that if a series' absolute value is convergent, therefore it's regularly convergent, and it's called absolutely convergent, if that's the case. So if this is true, the series is called absolutely convergent. And if a series is absolutely convergent, then it is also plain old convergent. So let's actually go with that. Let's actually prove that it's absolutely convergent, and then I'll use that to prove that it's plain old convergent instead of using an alternating series test. So if I consider the series absolute value, well, then I know that alternation goes away, and I'm just left 1 over 3 to the n. And this, I know, I could rewrite it if I wanted to as 1/3 raised to the n. And I recognize both of these as geometric with a common ratio of 1/3. And since 1/3 is less than 1, I know that this series converges by geometric series. What you've just done here is you have just proven that the series from 1 to infinity of negative 1 to the n plus 1 over 3 to the n is absolutely convergent. And therefore, if the series is absolutely convergent, it is also convergent. So that's proving convergence through absolute convergence. So that's the only test that I have for you guys today. I did want to take a moment just to revisit part F of that last example. And we can take a look at this one. So remember in part F, we proved that this converged by alternating series test. But now consider the absolute value. If I consider the absolute value, then this negative 1 to the n plus 1 would become a 1 over n. And this series diverges by p series. And since its absolute value doesn't converge, it is not absolutely convergent. And we can add on that the series converges by AST, and therefore the series is conditionally convergent as well. When I did that absolute value test. Let's also take the opportunity to go back and look at part E as well, because notice that alternating series test was not conclusive because it failed this decreasing for all values from 1 to infinity issue. So let's, I'm going to need some more space. So I'm actually going to take this and I'm going to go down. Actually, that should be good. That'd be perfect. All right, so I need some more space. So let's just consider it again. So I had the series from n equals 1 to infinity of negative 1 to the n all over n minus 5 squared plus a 1. Was it negative 1? Yeah, negative 1 to the n. Okay. So now what I want to do is let's do the absolute value test. Let's try and prove absolute convergence. Because if I can prove that this absolutely converges, then I know that it plain old converges. And that would be grand. So I've got the sum from n equals 1 to infinity of 1 over n minus 5 squared plus a 1. So let's think about maybe a comparison that I can do. And I'm seeing that n minus 5 squared plus 1, and I'm thinking no direct comparisons. I don't want to mess with that. So let's do a limit comparison test, and let's compare with the sum from n equals 1 to infinity of 1 over n squared. And this I know converges by a p series. So now all I have to do is determine that the limit as n approaches infinity of 1 over n minus 5 squared plus 1 all over 1 over n squared is finite and positive. And if I have that, I've got everything I need. So I'm left with an n squared over n minus 5 quantity squared plus 1. So I don't have to multiply this out. If I do, I know that that front leading term will be an n squared, and that will be my highest power. Therefore, the limit as n approaches infinity would just be the quotient of its leading coefficients, which is going to be a 1, since I have 1's up there. And 1 is definitely finite. It is definitely positive. Therefore, I know the sum from 1 to infinity of 1, let's just start with 1. Let's actually just go all the way through. 1 over n minus 5 squared plus 1 will converge by the LCT. And since I've proven that, I know that the sum from n equals 1 to infinity of negative 1 to the n all over n minus 5 squared plus 1 is absolutely convergent. Meaning, I can also say, and therefore, it is also convergent. So you can see there how we're bringing in some of those older tests, so you can see how if one test doesn't work, it's not a huge deal. You just got to think back to your toolbox and pull out a different test that might work that's going to better fit your conditions. All right, only one more video to go, everyone. We've got a ratio test and a root test in the next video, and then you are done learning all of your tests.